Hello, I'm Jonathan Weinberger, currently at the Max Planck Institute for Mathematics in Bonn. Today I'm going to talk about synthetic fibered infinity one category theory. This is based on joint work with Ulrik Buchholtz. You can find our joint preprint here, and also on my recent PhD thesis written at TU Darmstadt, also in Germany, supervised by Thomas Streicher. So let's start with the idea of an infinity one category. So as opposed to an ordinary category, in an infinity one category, we're dealing not just with sets of morphisms or arrows, but with spaces of such. And moreover, composition is now not defined as an operation strictly given on the nose, but it's something weaker. So it's only defined uniquely up to contractibility. So as a picture, we could think of the following, namely a pair of composable arrows. Then let's look at the composition data. And this is given by a third edge, and then something like a higher morphism or a two-cell, witnessing that this third edge is actually the composite edge or a composite edge of the two arrows. And this composition data now forms a whole space worth of data, and we demand that this be contractible. So this is the sense in which we can make a kind of weak operation out of composition. So infinity one categories have been introduced as implemented as quasi-categories in the 70s and later considerably developed by Riehl and Shulman. They come up in places in algebraic topology, homotopy theory, algebraic geometry, and other areas as well. So despite this intuitive picture, it's actually quite hard to define precisely what an infinity one category is. In fact, there are many different mathematical implementations or models of this concept going under various names, and they tend to be quite different to work with in style and setting. So the principal situation could be summarized by saying that when working in our usual set theoretic foundations, we sort of have to work analytically, meaning we have to build those more complicated higher homotopical structures out of just bare sets, which don't really have any structure at all. So we could now ask, is there maybe a more convenient, a synthetic way to reason about infinity one categories? Could there be a new foundational system in which the basic objects already have some intrinsic homotopical structure such that we can rather easily define those higher categories out of them? So to work our way towards such a theory, let's look at what's called Martin-Lof type theory. So this is a logical system in which one can formalize mathematics. It's a bit older. It's from the 1970s, and it consists of it's a system of derivations of judgments involving the following basic entities, namely types, terms of such a type, and contexts, which are finite lists of variables, so to speak, or term declarations. So in comparison to set theory, the role of sets is going to be played by the types, and the role of elements roughly is played by the terms of a given type, but they do behave quite differently in many ways in comparison or in contrast to set theory. I also want to consider what's called a dependent type or a type family. So we can say that a type family A depends on a context gamma. For instance, we could consider the type family of finite dimensional standard real vector spaces indexed by dimension. And we can consider terms or sections in such a type family, such as the family of zero vectors, where we pick out the zero vector in each dimension. So in type theory, we can also we can also make the judgment that certain terms or types are equal in a rather syntactic sense. So this is called judgmental equality, and basically means we can rewrite a term or a type into another one such, given a certain set of rules. But there is a more intricate notion called propositional equality, which gives us a new type for any pair of terms, which is supposed to capture the proofs, or in a geometric picture, the paths, if you will, connecting two terms with one another. And this family of identity types endows each type with the groupoid structure in a rather canonical manner. But furthermore, this can also be iterated, because an identity type is in particular again a type. So first, starting with identities between terms, we can also look at identities between identities, identities between identities between identities, and so on, up to the infinite. And this has, in fact, been considered semantically. So first in '94, Hofmann and Streicher came up with the one groupoid model, which in particular showed that even for self-identities, because of the presence of non-trivial automorphisms, we do get non-unique inhabitants of such an identity type in general. And later in 2006, independently suggested by Wygotsky and Streicher, it was conceived that we could, in a precise way, implement types as higher groupoids using Kahn complexes. So this led to the genesis of what's called homotopy type theory, HoTT, or univalent foundations, UF. So those are extensions of Martin-Lof type theory, allowing for doing synthetic homotopy theory. And particularly in beginning 2006, and in the later years, there was very ground-laying work by several people. In particular, Wygotsky introduced what's called the univalence axiom. And in 2019, there has been another milestone achieved by Mike Shulman, who showed that, in fact, any infinity one topos, in the sense of Grothendieck, Rezk, and Lurie, gives rise to an interpretation of homotopy type theory, making HoTT a kind of internal language of any higher topos. So the slogans or the basic principles that one should take away here about HoTT are the following. So types are homotopy types or infinity groupoids. Dependent types arise as fibrations. Propositional identities are interpreted as paths. And isomorphic types are equal, which roughly is the statement of Wygotsky's univalence axiom. So dependent types being fibrations can be depicted as follows. Consider a family P over a type B. Then we can lift any given path U in the base, assuming that we're given a point E and the fiber of the starting point. So we recover a sort of famous path lifting property from homotopy theory now, which is captured here synthetically in the type theory. In particular, this really makes definable the ensuing transport map. But what about synthetic infinity one categories in HoTT? So we said that types are interpreted as infinity groupoids, but infinity one categories are much more general. In particular, we have to be able to capture the directed Hom types and not just the sort of undirected path types. So one approach, independently suggested by Riehl and Shulman, is to extend HoTT to reason about simplicial types or simplicial spaces. And in fact, Riehl Shulman have taken up on this suggestion and defined an extension of homotopy type theory, giving rise to simplicial HoTT. And in this extension, one can internally single out those types that are in fact infinity one categories or infinity groupoids. And by Shulman's result from 2019, we can in fact interpret this internally to an ambient arbitrary higher topos So this gives rise to synthetic internal infinity one category theory. So our contribution consists of developing fibered infinity one category theory in this setting, namely simplicial HoTT due to Riehl Shulman. And we're very much guided by real verities infinity cosmos theory, which is another way more general approach to higher categories, but which is itself not based on type theory, at least not in this sense. So let's look at this language called simplicial HoTT. So as usual, types A can depend on type context gamma, but they now can depend on additional contexts as well, written as psi and phi here. And these contexts are, they do contain some additional shapes such as the simplices or similar shapes. So there's a very precise syntax for this, but let's not dwell on this any longer, but instead look at some pictures. So first, a very basic shape that we can have is just a directed interval like this. We can take powers of those, giving rise to the square or some higher cube. And we can also look at the simplices, such as the two simplex here, or the two one horn, or higher horns, and also other shapes that are definable in this specific theory, but sort of all based on subshapes of cubes. So another gadget that we introduce are the so-called extension types. So these can be understood as sections with strict side conditions. Namely, consider the following as input. We start with the shape inclusion, as we see down here. We consider a family P lying over the larger shape, and we consider what's called a partial section. So that's a section of the family, but it's defined on the smaller shape called A. And now we're interested in those sections defined on psi that strictly extend A. So we're interested in terms B defined on psi and landing in the corresponding fiber at P, such that when restricted to phi, they strictly coincide with A. So semantically, this can be modeled as a pullback, but the point to introduce this as an extra gadget in the theory is to really have here this strict computational behavior. So how can one define synthetic infinity one categories with this? So first of all, Riehl Shulman defined directed Hom types via these extension types, basically by using functions from the one simplex that appropriately restrict on the boundary like this. So these are just the basic Hom types, and they also have a dependent version, which can be defined in the syntax, but let's look at a picture instead. So given a family P over B like this, we can look at an arrow W in the base, then we can look at the type of arrows lying over it, like this H here. And we can do so similar for other shapes like the horn or the two simplices that we see here in this picture. So now Riehl Shulman defines synthetic infinity one categories as follows. So synthetic pre-infinity one category, or a Segal type, is defined as a type which is local with respect to the two one horn inclusion into the two simplex. And this precisely means that this type has a weak composition operation. So the two one horn is just the pair of composable arrows. And to get actual infinity categories or Rezk types, we have to add a further completeness condition, which says that the two conceivable notions of identity or isomorphism coincide, namely the one given by the type theory, the propositional identity type coincides with the type of isomorphisms, where the latter is defined in terms of the Hom type via bi-invertibility. And synthetic infinity groupoids in this sense arise by the discreteness condition, which says that every arrow, so every term of a Hom type is invertible. Okay, so let's work our way towards the definition of a Cocartesian family. So the idea, first of all, is the following. Recall that any type family, in fact, transforms covariantly in paths. So any path like this via lifting introduces a transport function, and we can ask to extend this for a similar operation, but starting from directed arrows. And Riehl and Shulman, in their paper where they introduce simple SHOTT, they develop a theory about discrete covariant families. So those are functorious families with this behavior here, whose fibers are synthetic infinity groupoids. And we have generalized this to the categorical case, giving rise to the notion of synthetic Cocartesian family, where the fibers are now Rezk. And in my thesis, I'm also providing some further extensions to this. So to establish this notion, we first need the notion of Cocartesian arrow. So consider a family P over B and an arrow U in the base. Then an arrow F lying over it is called Cocartesian if it satisfies the following universal property. So for any V that we can post-compose within the base, and for any H lying over the composite, there is to exist uniquely up to homotopy a G that fills this horn here and gives rise to a composite 2 simplex. So this picture might be familiar if you've seen, for instance, fibrations, Grothendieck fibrations of 1 categories before, but the point is now that we can define this in this syntax here using the usual type theoretic connectives, this contractibility predicate, and these extension types from the extended type theory. So we don't have to analyze this further, but please just note that it's possible to define things like this in this theory. So a Cocartesian family is defined as follows. First, consider a family over a Rezk type, all of whose fibers are Rezk. Then it's Cocartesian if every arrow has a lift lying over it that is Cocartesian under the assumption or under the additional data that we're given a point over in the fiber over the starting point of this arrow. So we can lift any U to an arrow lying over it with a prescribed base point. And please also note that one can show that this Cocartesian arrow, if it exists, is going to be uniquely determined up to homotopy as well. And this gives rise to a transport operation, which on arrows acts as follows. So given an arrow in the fiber over here, we want to see how it gives us an arrow in the fiber over B. Well, by looking at the Cocartesian lifts, we can just get this arrow by the universal property here. And semantically, those Cocartesian families correspond to what one might expect, namely covariant covariant infinity 1 category valued functors on a small infinity 1 category. So we've proven several things about Cocartesian families in this setting, for instance, the following characterization. So given a type family over a small Rezk type, all of whose fibers are Rezk, this family is going to be Cocartesian if and only if in the following situation there exists a left adjoint right inverse, namely consider the inclusion of the starting point into the interval. This induces a canonical square using the fibration or the family. And we can look at this mediating map here. This is supposed to have a left adjoint right inverse. And if and only if this is the case, then the family is going to be Cocartesian. And the idea is that this map precisely is the lifting map, which lifts the given initial data to a Cocartesian arrow in the fibration or in the total space. So this is called the Chevalier criterion in more traditional settings. It has also been proven in the very abstract and way more general setting of infinity cosmos theory by Riehl and Verity. And what's nice about this here in our type theory is that it implies a lot of closure properties that we can internally prove in this type theory for these Cocartesian families. We've also proven a Yoneda lemma for Cocartesian families. So this is a fibrational form of the Yoneda lemma. And it can be stated by saying that the Cocartesian arrows, the Cocartesian functors from a co-representable fibration into a family correspond to the points in the fiber, as one might expect. And for those who are more type theory minded, you might take a look at this version, the dependent Yoneda lemma, originally established in the discrete case by Riehl and Shulman, which is a kind of directed arrow induction principle, generalizing the directed path induction principle, the path induction principle of the identity types. So to give an overview about some further developments, well, up to now, we've discussed Cocartesian families. And in my thesis, I've considered variants of those, namely bicartesian families, which are both covariant and contravariant. And furthermore, I've considered the case that those bicartesian families or bifibrations have well-behaved extensive internal sums, which gives rise to some nice results to consider, generalizing some classical results due to Moon's Benabou. And then furthermore, I've also considered a fibered variant of those fibrations. So these would be fibered functors like this, satisfying a certain lifting property. Those are of, in particular, of technical relevance when considering what's called two-sided Cartesian families. So those are families which depend on two variables, on the first covariantly on the first one and contravariantly on the second one. And furthermore, I've also given the proof of some semantic fact that is needed when giving an actual interpretation function in a model structure coming from a higher topos. And this corresponds to the strict stability under substitution of these extension types here. So I'd like to conclude with an outlook on some future work and work in progress. So we're interested in, for instance, getting the Rezk type of small Rezk types into this theory. Namely, we want to have a theory of Rezk universes, and we'd also like to import some familiar categorical gadgets, such as opposite types or twisted arrow types, to, for instance, recover the more classically known version of the Yoneda lemma in an indexed variant. But yeah, these features sort of require more enhancements to the type theory, so it's they're not really definable right away. And one very nice application of this would be the development of synthetic higher algebra in this setting. So out of the major references, let me point out specifically the original Riehl and Shulman paper here and the recent book by Riehl and Verity on infinity cosmos theory. And on that note, I'd like to say, I'd like to leave it and say thank you for your attention. So if you've gotten curious and want to read up some more, or like to reach out, you're invited to take a look at my webpage. Thank you very much.